Good morning. I'll continue the discussion on cascade analysis. So the content of the lecture are effect of viscous flow. I will define today what is called blade efficiency or diffusion efficiency. Here I'll discuss on both compressor and turbine cascades. I've already discussed about the effect of viscous flow. Because of viscous flow passing to a cascade, there will be a decrease in total pressure between inlet and at a station well downstream of cascade. And the loss in total pressure can be defined as omega tilde equal to P01 minus P02, where P01 is the total pressure at the inlet and P02 being total pressure at the exit of cascade. After this, we can define now the blade efficiency or diffusion efficiency. Now let's begin with a compressor cascade. For a compressor cascade, the static pressure rise is reduced due to viscous effect. We already know that for a compressor cascade, there will be decrease in velocity because flow will decelerate, and thereby there will be rise in static pressure. However, this rise in static pressure will be reduced because of viscous effect. Thus, the blade efficiency can be defined here as eta B for compressor cascade is equal to actual rise in static pressure divided by ideal rise in static pressure. For a compressor cascade, ideal rise in static pressure will be higher than the actual rise. Thus, I can write eta B is equal to P2 minus P1 ideal minus loss divided by P2 minus P1 ideal, where P2 is the exit pressure, static pressure, and P1 is equal to inlet static pressure, inlet to the cascade. Now here I'll try to derive the analytical expression for eta B. So let us consider a compressor cascades and C1 be the inlet velocity and C2 be the exit velocity, where C2 is less than C1. And as before, this is the axial direction. And Cz must be the same as the mass flow rate is constant. P1 is the pressure at inlet and P2 be the pressure at exit to the cascade. Now alpha 1 be the angle that C1 makes with the Z axis, and alpha 2 similarly be the exit absolute flow angle. Now with this input, let me draw the velocity triangle I have already explained earlier. Still, let me repeat here, I have superimposed the velocity profile both for the inlet and for exit. And C1 here, the inlet velocity. C2 is the exit velocity. Alpha 1 is the absolute flow angle in inlet. Alpha 2 absolute flow angle at exit. And thus I have evaluated Cm be the vectorial mean velocity, and Cm makes an angle alpha m with the z axis. This is alpha m, and Cz is the velocity is the axial direction. C theta is the peripheral component of velocity. So I have defined here C theta 1 and C theta 2. And del C theta is nothing but C theta 1 minus C theta 2. After appreciating the velocity triangle, I can come to the expression for eta b. Eta b now is the ideal pressurized minus loss divided by ideal pressurized for a compression. Loss is given by the quantity omega tilde, and ideal pressurized can be stated at half rho C1 square minus C2 square. So I have stated here eta b equal to half rho within bracket C1 square minus C2 square minus omega divided by half rho within the bracket C1 square minus C2 square. Thus it can be written as 1 minus omega tilde divided by half rho within bracket C1 square minus C2 square. Now from velocity triangle I can write C1 square is equal to C theta 1 square plus Cz square, and so as to C2 square. And thus if I do C1 square minus C2 square, I'll get C theta 1 square minus C theta 2 square. And thus it would be C theta 1 plus C theta 2 divided by C theta 1 minus C theta 2. Now, if you substitute the value of C1 square minus C2 square in the expression of eta b, you will get this, which is eta b is equal to 1 minus omega tilde divided by half rho C theta 1 plus C theta 2 into with bracket C theta 1 minus C theta 2. Right? Now here I have done some algebraic manipulation. Now in the expression of eta b, look in the second part. Both numerator and denominator I have multiplied by s into cos alpha m, and denominator I have grouped the terms. Suppose rho s C theta 1 minus C theta 2 I have grouped as one block, and the second block I have grouped as C theta 1 plus C theta 2 divided by 2 into cos alpha m. Now look here, this is the velocity triangle. Please concentrate on that velocity triangle. And here in the velocity triangle, say suppose I have defined del C theta. Del C theta is nothing but C theta 1 minus C theta 2. And while defining Cm, I have already told that del C theta I have divided, equally divided. Okay, so this is del C theta divided by 2. And these, if you take this length, this will be c theta 1 plus c theta 2 divided by 2, right? That I have explained here from velocity triangle. What I have stated c theta 2 plus del c theta by 2 is equal to c theta 1 minus c theta 2 divided by 2 plus c theta 2. It's becoming c theta 1 plus c theta 2 divided by 2. So therefore, this c theta 1 plus c theta 2 divided by 2 is equal to Cm into sine alpha m. So this length will be equal to Cm into sine alpha m, right? Furthermore, gamma circulation is equal to S within bracket c theta 1 minus c theta 2 for a compression. Now put the value of gamma, and this bracketed quantity is equal to Cm into sine alpha m. Put that too. So this expression would be eta b equal to 1 minus omega tilde s into cos alpha m divided by rho gamma into Cm sine alpha m into cos alpha m. Now look, omega s into cos alpha m is drag. So this is drag, right? Now rho gamma into Cm, this would be equal to lift if we neglect the effect of drag. So here I have made an approximation that in the expression of lift, I have neglected the effect of drag. So I have considered here lift is equal to rho gamma into Cm. Thus, eta b would be 1 minus d divided by half L into sine twice alpha m. Therefore, the blade efficiency for a compressor casket can be given by eta b equal to 1 minus twice CD by CL into sine twice alpha m. This is an important relation which will give us blade efficiency for a compressor casket is equal to 1 minus twice CD over CL into sine twice alpha m. Here an approximation has been done considering that lift is equal to rho gamma into Cm. Thus in expression of lift we have neglected the effect of drag. Now one can appreciate that blade efficiency is function of alpha m and the ratio of CD by CL. For a given blade profile, CD by CL ratio becomes finite. Thus, for a given profile, the blade efficiency depends on alpha m. Now, for maximum blade efficiency, d eta b by d alpha m must be equal to 0. So by that, I can evaluate the condition for maximum blade efficiency. I have differentiated here eta b and equated to that equal to 0. and that leads to cos twice alpha m is equal to 0, and thus alpha m is equal to 45 degree. Thus the value of mean vectorial angle for the maximum blade efficiency becomes 45 degree for a given blade design. Now here I have plotted the variation of eta b with respect to alpha m. It has been realized that eta b illustrates a larger flattened region, so thus almost in the range of 15 degree to 75 degree of alpha m. Eta b does not vary much, which illustrates the flexibility in design. Now I derive the expression for blade efficiency of a turbine gasket. Please remember that for a turbine gasket, drag is a useful component. Thus, in a turbine gasket, actual static pressure drop will be higher than the ideal static pressure drop. Thus, I have defined blade efficiency for turbine gasket as ideal static pressure drop to give a certain change in kinetic energy divided by actual static pressure drop to produce the same change in kinetic energy. Thus, eta b I have defined as del Ps ideal. Del Ps means change in static pressure divided by del Ps actual. Here I have indicated the velocity triangle. Now we are aware of the flow will accelerate as it will pass through the gasket, turbine gasket. The C2 will be higher than C1, and thus alpha 2 will be greater than alpha 1 that I have shown here. So C1 is the inlet velocity, C2 is the exit velocity, alpha 1 is the absolute inlet angle, and alpha 2 is the exit angle, and thereby I have defined Cm and alpha m. Okay, so this is the velocity triangle for a turbine gaskets. Thus, the eta b would be down here. Eta b is equal to half rho C2 square minus C1 square, because C2 is greater than C1, divided by half rho C2 square minus C1 square plus omega tilde. Omega tilde is the loss component that can be written as 1 over 1 plus omega tilde divided by half rho within the bracket C theta 2 minus C theta 1 plus again within the bracket C theta 2 plus C theta 1. Just as before, right? Now, following the derivation earlier, it can be written as eta b equal to 1 divided by 1 plus twice CD by CL, 1 divided by sine twice alpha m. So this is the expression for eta b for turbine gasket. Now I'm Here, going one step more, for small value of CD by CL, indeed in reality the ratio of CD by CL is small, then we may consider the turbine efficiency eta B equal to 1 plus twice CD by CL 1 divided by sine twice alpha m to the power minus 1. That would be equal to 1 minus twice CD by CL into 1 divided by sine twice alpha m. So this expression is now same as that of compressor cascade. Thus please note that for small ratio of CD by CL, the blade efficiency for turbine would be the same of that of the compressor. However, in the expression here, in the lift coefficient, I have neglected the effect of drag. Now, if we consider the effect of drag in the expression of lift, then the blade efficiency would be as eta B for the compressor equal to 1 minus CD by CL into cot alpha m divided by 1 plus CD by CL into tan alpha m, while the eta B for the turbine cascade would be 1 minus CD by CL tan alpha m divided by 1 plus CD by CL into cot alpha m. Please note the difference. Thank you for listening.